This is the last lecture from Chapter 4. It's about a type of reaction called an oxidation-reduction reaction. Oxidation-reduction reactions are reactions where electrons are transferred from one substance to another. You'll also hear these called redox reactions. Oxidation occurs when one of the substances loses an electron. Reduction occurs when the substance gains electrons. I've always felt like those definitions are opposite of what they should be, but and they occur simultaneously. Obviously, if a substance is going to give up electron, there needs to be another substance that will accept it. Here's a memory trick that I've always used to remember, keep these two straight. Leo says Gur. So lose electrons means oxidized, gain electrons means reduced. So probably the most simple oxidation-reduction reaction would be the formation of an ionic compound or salt, for example. So if we start with neutral sodium and neutral chlorine, and under the right conditions, combine them so they produce sodium chloride. Sodium chloride, of course, is actually an ionic compound made up of a cation and an anion, and so it's pretty easy to look at this reaction and see that the sodium metal has given up an electron to become a cation. So sodium metal has been oxidized, lose electron, oxidized, and the chlorine has become negative, so it has gained an electron. In other words, it's been reduced. It's not always going to be that obvious to either identify whether it's a redox reaction, and once you've identified that, to know what's been oxidized and what's reduced. So the rest of this lecture is really kind of going through how do you identify a redox reaction. All right, so we use something we call oxidation numbers. We assign every single atom, every single element in a chemical reaction what we call an oxidation number. And then we look from the reactants to the products and see if any of the oxidation numbers have changed. If they have, it's a redox reaction. So the first thing I want to say is that oxidation numbers are not charges. They're going to look like pluses and minuses. They're not real. It's kind of a bookkeeping method. It may give you an indication of where electron density seems to be focused, but keep in mind, it doesn't, just because it has a plus or minus sign doesn't mean that in reality that's a charged species. So before we start assigning oxidation numbers, there are a couple rules that I want you to be aware of. You may want to jot these down. And the first one is the sum of all of the oxidation numbers of the elements that make up a compound must add up to be 0. So let's look at sodium chloride. Overall, its overall charge is 0, okay? But we know that the individual charges, sodium is +1, chlorine's -1. But when you add those together, +1, -1, you get 0. So same thing with assigning oxidation numbers. When you add them all together, you need, if it's a neutral compound, they need to add up to be 0. The second rule, elements in their standard form have an oxidation number of 0. So when I say standard form, what am I talking about? That's how it exists in nature. So remember the 7 diatomics, they exist as two of them. And so this chlorine in this form would have an oxidation number of 0. Sodium would have an oxidation number of 0. Okay, the third rule is if you are dealing with an ion, the oxidation number of that ion is identical to its charge. So if we're talking about the sodium cation Na+1, its oxidation number is also +1. All right, so these are just kind of some trends. Well, the next one is kind of a trend. So nonmetals, remember those are the ones to the right of the stair step on the periodic table. They tend to have negative oxidation numbers. Not always, though. You will actually see cases when halides have positive oxidation numbers. One thing that you can count on is if you have a fluorine in a compound, it always has an oxidation number of -1. The rest of the halogens usually have an oxidation number of -1, but as I said a minute ago, they can actually have positive oxidation numbers. Here's probably the most important rule of all of them. Oxygen almost always has an oxidation number of -2. That's really important to know because that's usually how you get started assigning oxidation numbers. There is one exception. If you have a peroxide, which is a oxygen-oxygen single bond, the oxygens only have an oxidation number of -1. I will not test you on that, but it's something that could conceivably show up on your final. All right, so hydrogen almost all the time has an oxidation number of +1. Again, there's an exception, but you're not going to see it from me. When hydrogen is bonded to a metal, it's almost always bonded to a nonmetal, but if it is bonded to a metal, it has a -1 oxidation. But again, you're not going to see that from me. All right, so let's go ahead and look at some reactions. I just noticed a typo. There we go. So here's a real simple one. Remember the rules, and if you haven't jotted them down, you may want to go back and jot them down. Elements in their standard state have an oxidation number of 0. Okay, so both of these reactants have an oxidation number of 0. And I go ahead and write the oxidation numbers above each element so that they're easy to compare from the reactant to the product side. And go ahead and write the oxidation number for one of the atoms. So in this case, for example, we have 2 chlorines. Well, 2 times 0 is still 0, but write it for just one of them. So here's sodium. We know that in sodium chloride it's an ionic compound, so we know there are actually charges. And one of the rules is ionic compound, the oxidation number is the same as its charge. Okay? Don't pay any attention to any coefficients at this point, okay? Just ask yourself, what's the oxidation number of that element in the compound? And again, this one's real easy to see. After you assign oxidation numbers, you want to look at what's happened between the reactant side to the product side. And this is where students tend to get mixed up. You've gone from a 0 oxidation number to a +1. What does that mean? That means that you have actually lost an electron. If something ends up positive, you've taken away a negatively charged electron. Feels counterintuitive, so be careful with that. So sodium has been oxidized. Remember Leo, lose electrons, oxidize. And if something's been oxidized, there's got to be another element that's been reduced. And in this case, it's chlorine. Chlorine has gone from 0 to -1, so it has gained an electron. Gain electron reduced. So here are some examples. At this point, get your rules together, shut off the video, and see if you can assign oxidation numbers to each of the elements in this compound. You may actually need to watch me do the first 2 of these to get a handle and then try it yourself. So let's look at CO2. So where do we start? I don't know if you remember, but when I was telling you the rules, I said the rule that's probably the single most important rule that'll help you is that oxygen pretty much always has an oxidation number of -2, unless it's a peroxide, which I'm not going to give you. So start by doing that. So you want to write the oxidation number above the element. So we're going to put -2 above the oxygen. Now, if there's a subscript, if there's more than one of the element, it does not affect the oxidation number. This -2 stays. However, remember the rule that at the end you've got to add together all the oxidation numbers and they must equal 0? Okay, so because of that, we need to kind of keep an addition tally going of the total oxidation number values. So because we have 2 oxygen, the 2 oxygen contribute -4 to the overall oxidation number. And so because the overall oxidation numbers have to add up to be 0, if the 2 oxygens give us -4, that means the carbon has to be +4 so that they add up to be 0. So I'm going to put +4 up here. All right, so let's go ahead and try nitrate. So the one hint I will give you, nitrate is a polyatomic ion. It is not neutral overall. It has a -1 charge overall. So when you assign oxidation numbers to oxygen and nitrogen, they must add together to give you -1. So keep that in mind. If you think you might be able to do it yourself, go ahead and turn off the video and try. Otherwise, you can wait to the next one. All right, so you're going to find that you start with oxygen most of the time. I'm going to start by giving oxygen a -2 oxidation number. Then I'm going to do my tally at the bottom here. I have 3 oxygens, so the oxygen, all 3 contribute a -6. So nitrogen has to have a charge so that when oxidation number, so that when I add it to -6, I get -1, which is the overall charge of the nitrate. So what -6 is -1? That would be +5. So the oxidation number of nitrogen is +5. Now definitely make yourself turn off the video and see if you can do the last 2 by yourself. All right, let's look at iron 3 oxide. So the easiest way to do this is to realize that that is an ionic compound. How did I know that? Because it consists of a metal and a nonmetal. Ionic compounds contain ions. And when you have ions, their oxidation number is simply equal to their charge. So the easiest way to do this is just figure out or figure out what the charges are on the ion and the oxygen. So if you do your little reverse cross or however you go about that, you see the iron in this compound has a charge of +3, which means its oxidation number is +3. Oxygen, as always, when it's an ion, has a charge of -2, which means its oxidation number is -2. So if you realize that was an ion, it makes it much simpler. If not, you can still figure it out. Okay, the last one. One of the rules was fluorine, unless it's an element on its own, always has an oxidation number of -1. I'm putting it in the wrong spot. Let's see. All right, so fluorine has an oxidation number of -1. Because there are 6 of them, they contribute totally to the oxidation numbers of -6. And because all of the oxidation numbers need to add up to equal 0, because sulfur hexafluoride is neutral, means that sulfur has to be +6 oxidation number. All right, that's it for that. Now we're going to look at actual redox reactions. So keep in mind there are a couple type of reactions that are always redox and then some that are never redox. So that'll really help you on the test. Combustion reactions are always redox reactions. If you're still shaky on how to write out a combustion reaction, remind yourself you need to be able to identify combustion, you need to be able to write them out and balance them, you need to know them. So hopefully you could be able to look at a reaction like this and say, oh, that's a combustion reaction because it has oxygen as one of the reactants and carbon dioxide and water as the products. And once you identify as combustion, you can say, okay, I know that's a redox reaction. Okay, so it might save you some time. So, but let's go ahead and go through the process of assigning oxidation numbers. Let's say you weren't sure it was a redox reaction. If you're not sure, you have got to assign oxidation numbers and look to see that if any of the oxidation numbers have changed. All right, so we're going to start with methane, CH4, and hydrogen has an oxidation number +1 always for our purposes. And there are 4 hydrogens, so they contribute a +4. And because the oxidation numbers have to add up to be 0, that means carbon must be -4. Oxygen, that's an element in its natural state, and they always have an oxidation number of 0. Right? Let's look at carbon dioxide. Oxygen, we always give it a -2. There are 2 oxygens, so collectively they contribute -4. And because the oxidation numbers have to add to be 0, that means carbon must be +4. Okay, +4 -4 is 0. Should do that here too. There. And now let's look at water. Give oxygen a -2. And so in order to add up to be 0, let's see, -2. In order to add up to be 0, the hydrogens together must be +2, because +2 -2 is 0. And since there are 2 hydrogens, if they collectively add up to be +2, each one is +1. So at the top, you're writing the oxidation number, remember, for just one of the atoms, okay? Now you can compare oxidation numbers from the product side to the, from the reactant side to the product side, and that's how you identify what's been oxidized and what's been reduced. They have to change from the reactant side to the product side if it's a redox reaction. So let's look a minute at all the oxidation numbers we have at the top. Okay, not the collective ones at the bottom, but for the individual elements. Which ones of those have changed? Has carbon changed? Why, yes, it's gone from a -4 to a +4. What happened to the electrons? Did it lose them or gain them to go from oxidation number -4 to +4? It lost 8 electrons. Remember, electrons have a negative charge, so if you take them away, you leave what's behind with a positive charge. So carbon has been oxidized. Lose electrons, oxidized. Okay, that means something had to have been reduced. So let's look at hydrogen. It goes from a +1 to a +1. Hydrogen did not change. It is not oxidized to reduce. All right, the only element we have left is oxygen. It started with an oxidation number of 0. If we look at oxygen and the carbon dioxide, it's gone to a -2. So 0 to -2 means you have gained electrons. Okay, you've got more negative. So oxygen has been reduced. Just a couple more slides. All right, we haven't really learned about single replacement reactions yet, but just in case this sticks with any of you, it might help you. A single replacement reaction is simply when you have a metal on its own, a metal element, that kicks out some other cation. Okay, so in this case, it's kicking out hydrogen. So then the metal that was on its own ends up in a partnership and has kicked out something else on its own. But that's called single replacement. You don't need to know that for the test. But if you do happen to be able to identify them, they are always redox reactions. So, but let's say you don't remember how to identify them. That, as always, you'd have to assign oxidation numbers to each element and then compare. So we're going to start with hydrogen. Remember, halogens are usually -1, but a significant amount of the time, okay, that's my dog drinking water in the background, a significant amount of time, halides other than fluorine don't have to be -1. They're even positive sometimes. So I wouldn't start with chlorine. Start with hydrogen as a +1. And that means in order for all the oxidation numbers in hydrochloric acid to add up to be 0, chlorine does in fact have to be -1 in this case. Copper is an element on its own, so it has an oxidation number of 0. Moving to the product side. Let's do the easy one first. Hydrogen is element in its standard state, so its oxidation number is 0. I'm hoping you look at copper 2 chloride and say it's ionic. I'm just gonna, the charges are equal to the oxidation numbers. Okay, now he's eating. So the charges in copper 2 chloride, halogen's -1, copper's +2, because remember, you can anti-crisscross if you want. So there, we have oxidation numbers. So now let's compare the oxidation numbers going from the reactant side to the product side and see what's been oxidized and what's been reduced. Well, hydrogen has gone from +1 to 0. Definitely changed. Did it gain or lose? Okay, it got more negative, right? So it gained electrons, and therefore hydrogen in this case has been reduced. All right, means something had to have been oxidized. So chlorine goes from a -1 and it stayed -1. So chlorine has not been oxidized or reduced. Copper, on the other hand, has gone from 0 when it was by itself to to +2. Okay, so what's happened to copper? It has lost electrons, so copper has been oxidized. That's it. Okay, this hint at the bottom is an important one. It will save you a ton of time on a test. You should know how to identify double replacement reactions. We went over those. That's if you have a reaction where you have 2 ionic compounds that are reacting. That means it's double replacement. They are never, ever, ever redox reactions. So don't waste your time assigning oxidation numbers if you identify it as a double replacement reaction. Just say it's not a redox reaction. It's probably worth proving it to yourself. Go ahead and assign oxidation numbers, but also remember that. Alrighty, here is the most common type of question you're likely to see on your next exam about redox reactions. Ooh, I've left all the arrows out. So I would probably give you a series of reactions like this and say, identify all of the reactions that are oxidation-reduction reactions. And what that would mean is you have to assign oxidation numbers to all of the elements and see whether or not it's a redox reaction. So definitely at this point, turn off the video. There's only one more slide, and see how well you can do with these. Alrighty, so let's just start with A. This is an ion. Oxidation number, since it has overall +2 charge, but there are 2 mercury, each mercury has a charge or an oxidation number of +1. Let's see, hydroxide. The oxidation numbers of the oxygen and the hydrogen must add up to be -1, because that's the charge of the polyatomic. I'm going to, you can start with either oxygen or hydrogen. Well, oxygen is -2, hydrogen is pretty much always +1, and that works out real nice for us. -2 + 1 equals -1. They add it up to be the charge, which it needs to be. Moving on to mercury oxide, that is an ionic compound. Figure out the charges or anti-crisscross if you're pinched for time. So the mercury ion has a charge of +1, and oxygen a charge of -2. Now all we have left is water. Oxygen, here, let me get a different color pen. We give a -2, Each hydrogen has a +1. There are a total of 2 hydrogens, so we have a +2 for both of them. And then -2 equals 0, just making sure the oxidation numbers for water add up to be 0. Now we compare oxidation numbers on both sides of the equation. Mercury goes from a +1 to a +1, no change. Okay, let's look at oxygen. Goes from -2 to a -2, no change in oxygen. All we have left now is hydrogen. Hydrogen starts with a +1 here, and it also has a +1 in water. So this is not a oxidation-reduction reaction. Let's look at B. Okay, again, mercury is, I'm going to write in the bottom now, +1 each mercury. Tin, it's an ion, so oxidation number is the same, +2. On the product side, this mercury has an oxidation number of 0 because it's an element in its standard state. And I don't know if you know, mercury is the only metal that's a liquid. Interesting. Okay, so tin ion, oxidation number is the same as its charge, +4. So now let's see if this is a redox reaction. Mercury is going from +1 to 0. It has changed, and it has gained an electron. So mercury has been reduced, gain electron reduction. All right, what's been oxidized? All we have left is tin. It's gone from +2 to +4. It has lost electrons, so tin +2, well, here, to give the exact species that's been reduced and oxidized. The tin ion has been oxidized and the mercury ion has been reduced. So B, yes, is a redox reaction. All right, so at this point I've totally trashed this slide. I'm going to go to the last slide, the next slide, and go over the last two. All right, so looking at C and D. C, mercury +1, each of them. Sulfur, well, we're going to start by assigning hydrogen +1 as it always is. There are 2 of them. So sulfur has to be -2 in order for them to add up to be 0. Mercury is on its own again here, so 0. And mercury sulfide is ionic. We know sulfur is -2, means mercury has to be +2. And hydrogen ion here is an ion, so the oxidation number is equal to its charge. So let's look for changes. Mercury goes from +1 to 0. So mercury has been reduced, or the mercury ion. This species has been reduced. And hydrogen starts at +1 and ends up at +1, so hydrogen has not been. Sulfur goes from -2 to -2. It has stayed the same. So what on earth has been oxidized in this reaction? We've already established that the mercury ion has been reduced, but we've checked the other elements, hydrogen and sulfur, and they haven't changed their oxidation state. So this is a special case. I want you to pay close attention if you're drifting, where the mercury ion has been the one that's been reduced, but it's also the one that has been oxidized. Because if you look at mercury 2 sulfide, the mercury has gone from a +1 to a +2. So when mercury formed mercury sulfide, it was oxidized. So the very same substance has been both reduced and oxidize. That's called disproportionation. You don't need to know that name, but you do need to be able to recognize that that's possible. We're finally on the last one. I'm going to go kind of quickly. I've included this because the mercury 1 chromate can be kind of tricky assigning the individual oxidation numbers. So we already know that mercury has +1 oxidation number, and there are 2 of them, okay? Chromate is a polyatomic. So if that's the case of the polyatomic, go ahead and write it out with its charge. Okay, so we have the overall charge of the polyatomic, but you still have to determine the oxidation number of the elements that make it up. So I'm, as always, going to start with oxygen and give it oxidation number of -2. There are 4 oxygen, so totally together they combine to give an oxidation number of -8. And collectively, the oxidation number of chromium, plus the oxidation number of the oxygen have to equal -2, which is the charge on the entire polyatomic. So what number does chromium, what oxidation number does it have to have? It has to have +6, okay? +6 minus 8 is -2. So the oxidation number of chromium is +6. All right, looking at hydroxide. Ooh, good. Make some room here. Okay, looking at hydroxide, oxygen -2, hydrogen +1. So let me go ahead and add these at the top here now that I have some room. Okay, and looking on the product side, mercury 1 oxide is an ionic compound. Okay, CrO4, we just went through what the assigned oxidation numbers are. -2 and +6. Water, -2 and +1. Now let's compare everything. Mercury has gone from +1. It has stayed +1. Mercury has not changed oxidation numbers. Chromium has gone from +6 and it has stayed +6. Oxygen has gone from -2 in both cases on the reactant side and has stayed -2 on the product side. So let's see, hydrogen, +1 on the reactant side, +1 on the product side. No change in any oxidation numbers, so D is not a redox reaction. That is it. We have finished chapter 4.